So section 4.6 is going to bring a lot of the work we've done all together in one place. We're going to start graphing functions using calculus. Now, even though we're going to use calculus, I'm not going to take your graphing calculators away from you. You're still going to be able to use them, and I encourage you to use them. But we're going to use everything we have at our mathematical disposal at this point. So we worked with derivatives, increasing and decreasing, concave up, concave down, minimum points, maximum points, inflection points, lots of stuff. You should also have in your little back pocket, your arsenal of mathematical things, tricks, a knowledge about domains, understanding where functions are even or symmetric. Odd functions, odd symmetry, it's not quite as helpful because it's not as visually striking, but if you can spot that, that's great. We're going to plot horizontal and oblique asymptotes. Sometimes people call those slant asymptotes, vertical asymptotes, X-intercepts, Y-intercepts, critical points, where it's increasing and where it's decreasing. If you notice, boy, it's a long ways down before we get to the calculus. There's a lot of things you can do without any calculus at all. So let's put this together and work on some problems. We'll start with problem number 4, which is this. Now, what I encourage you to do when you're looking at these types of problems is first start with the domain. Are there any values of x that are going to create issues? Plus or minus 1. Good. Where the denominator is 0, where x squared minus 1 equals 0, that's where you're going to end up with issues. So plus or minus 1. So we're going to have to exclude those. So from our domain, it's a set of x such that x is not equal to 1 and x is not equal to negative 1. So let's get rid of those right away. One of the things you may or may not notice, depends on you. Now I wrote this as f of x equals this. In the book they wrote it as y equals this. But this is more convenient. If you might notice that f of negative x equals f of x, that is if I put in a negative here, negative x squared plus 1 over negative x squared minus 1. If I put in those negatives like that, well, squaring negative x and squaring x are the same thing. So that tells me it's an even function. What does that say about the graph? Do you remember what even functions look like? Cosine's an even function. X squared's an even function. They're symmetric with respect to the y-axis. Good. So symmetric with respect to the y-axis. It should be a mirror image of itself around the y-axis. Just something to keep in mind as we look at this thing. Now, let's get down to some of the more important stuff. Some of the stuff that's really going to be handy. This is a rational function. What case are we dealing with on our handout? Case B, right? The degree of the numerator equals the degree of the denominator. So if that's the case, then we get y equals a over b is the horizontal asymptote. A and b are the coefficients, the leading coefficients of the numerator and denominator respectively. What's the horizontal asymptote here? Yeah, 1 over 1, or better yet, just 1. So y equals 1, that's going to be our horizontal asymptote. Let's actually add that to our graph. If you'd like, I've got rulers up here. Come on up and help yourself. So y equals 1. I'm going to fill that in with a dashed line because it's really not part of our graph. It's kind of a feature of the graph, but it's not a part of the graph of the equation. All right, so y equals 1. Okay. So that's actually steps 3 and 4. We graphed it. So we got the horizontal asymptote. What about the vertical asymptote or asymptotes? How do you find those? All right, set the denominator equals 0. Well, we kind of already did that, right? We know where the denominator equals 0. So at x equal 1 or at x equal -1, you're going to have vertical asymptotes. So let's add those to our graph as well. So now this really frames our graph. I mean, with this, it's hard to really go wrong too far when you're drawing your graph. Let's see what else we can come up with. Now, in the interest of time, let's see, that's 5 and 5. So we've graphed those. Oh, let's find out the Y-intercepts. X and Y-intercepts. How do you find the Y-intercept? Set x equal to 0. So if I set x equal to 0, and don't make Yezin do all the work here for us, what am I going to get for y? -1. So 0, -1, that's a point on our graph. To find the x-intercepts, you set y equals 0. With a rational function, this rational function equals 0 where the numerator equals 0. Can the numerator equal 0? Can x squared plus 1 equal 0? No. If you solve for it, x squared plus 1 equals 0, you get x equals square root of x. X equals the square root of -1, so it equals 1 only, or equals 0 only in your imagination, right? Because you get an imaginary number there. In the interest of time here, I'm giving you the first and second derivatives. First and second derivatives tell us what about a function? Increasing, decreasing, concave up and concave down. So with the first derivative, and actually with both of these, I want to know where these expressions can change signs. In other words, where the numerator equals 0, so that'll be one possibility, or where the denominator could equal 0. So where the numerator equals 0, or where the denominator equals 0. Let's start with the first derivative. Where could the numerator equal 0? 0. All right, so at x equals 0. How about where the denominator equals 0? -1 and 1. So you just kind of keep these color coordinated. Numerator equals 0 and denominator equals 0. So let's do ourselves a little bit of a t-table here. You've got x, f, and f prime. Now the derivative at x equals 0 is 0. What's the value of the derivative at x equal -1 and x equal 1? Undefined. All right, you've got vertical asymptotes there, so there's not even a point on the graph. But other than that, we can test the function at points in between these. Now, if you want to do that by entering that into your calculator and testing values there, that's fine. That's great. So let's test it this way. -4x divided by x squared minus 1 squared. Independent is set to ask. So go to your table function. Let's delete all these old values with the delete key. And now I need some test points. What would be some good test points for us here? All right, -2, -2, -1/2, 1/2, and 2. Let's not try and hurt ourselves, right? Just keep them simple. -2, -0.5, 0.5, and 2. What information am I looking to get out of this? Good. Yeah, negative and positive. All right, so positive, negative. No, wait, see. No, it looks like positive, positive, right? Positive, positive, negative, negative. Okay. So plus, plus, minus, minus. And that tells me that the function is increasing, increasing, decreasing, decreasing. Okay. Yes, nice observation here. If the function's increasing, increasing, well, increasing here and then decreasing here, there has to be a relative max near 0. So that's good to know. This is going to be a max. So let's try the second derivative. And you know what? Looks like I didn't copy down the second derivative. I just did copy, cut, and paste. Guess we're going to have to figure it out ourselves. I hate when that happens. Spend a lot of time making these handouts, and it's annoying. Do I have that in my notes? Let's see. No, I don't think it. There. Okay. Give it a Wolfram it. All right, let's practice with the Wolfram Alpha just for good measure. I think it'll help us out in this one. So the form of the command for the derivative is derivative of the function. So there'd be x, no, I need a parenthesis, x raised to the second power plus 1 divided by parentheses x raised to the second power minus 1, close parenthesis, close off the denominator, comma x. So this should be the first derivative. I'm going to show you a way that I cheat to get the second derivative. For the second derivative, I just type in derivative, parenthesis, and then comma x. So I take the derivative of the derivative. I'm cheating. All right, somebody likes that one. Some people call it laziness. I prefer to think of it as economy of movement. Yeah, efficiency. I like that. All right, so let's take a look at the second derivative. There we go. That's much better. That's what we should have. So 4 times 3x squared plus 1 over x squared minus 1 cubed. Boy, that's nice. All right. Let's copy that down. So 4 times 3x squared plus 1 divided by x squared minus 1 cubed. Hasta la vista. Now, like before, I need to know where the numerator equals 0 and where the denominator equals 0. Well, the numerator can't equal 0. 3x squared plus 1 will not equal 0. So this can only change signs where the denominator changes signs. And the denominator changes signs at -1 and 1. So let's enter some stuff in here. F double prime. Again, the function doesn't exist at these points. So let's test some values. We can use basically, now let's see, let's go -2, 0, and 2. If I can, let me just save us a little time here. I think it tests out to be plus minus plus. What's that telling me about my function then? Concave up, concave down, concave up. So wow. Now, we've gotten a ton of information about this. There's nothing at all that stops you from graphing this. I'm always surprised when I see somebody handing in a test and their graph looks nothing like what you could see out of a graphing calculator. Just nothing like it. I'm not sure why people don't double check themselves. You've got these nice $100 toys. If you don't have one, you can borrow one. But let's take a quick look at the graph and see if it confirms all of what we're going to see here. So let's clear this out because I want to look at the function, not its derivative. X squared plus 1 divided by x squared minus 1. And here's another little tip for you. I mean, not that you should use like all these tricks like kind of against me or against the test, but I'll help you out. How about if we set up the window to match what we have here, right? Might as well. So -6 to 6 on the x-axis, -4 to 4 on the y-axis. So -6 to 6, scale of 1, and -4 to 4, also scale of 1. All right. Matches everything that we looked for. Concave up, concave down, maximum point, horizontal asymptote, vertical asymptotes. It's got it all. So let's just try and copy that, sketch that roughly here. The only point that I'm really going to be critical about in this graph is that you should have the y-intercept correct. That's the only point that we're really working on plotting carefully. The rest of this, just try and estimate as best you can. There. And there. But that nails it. That's got everything that we would want out of this graph. Now, are all your functions going to have all these little details to take care of? No. But I'm trying to give you a good sampling of different things you're going to have to look at. Okay, we did a lot of stuff here on this first problem. How are we looking on that first one? Sweet, doing all right? Let's move on to problem number 30. A lot less detail that we're going to have to fuss with than problem 30. Not as nearly as many little things we're going to have to work on, pay attention to, but still some. So, next page, problem number 30. I'm going to help you out here. X squared plus 2x plus 2 is always greater than 0. So we're not going to have any problems with the domain of this function. Same thing over here. The domain is just everything. It's negative infinity, it's less than x, less than infinity. So the domain is everything. This is not a rational function. That's great. That means we don't have to mess around with any horizontal asymptotes and no vertical asymptotes as well. So we're okay in that regard. You can take time to plot the y-intercept. How would you find the y-intercept? Yeah, set x equals 0. So the y-intercept is going to have this coordinates 0 and 7 times the inverse tangent of 1. 7 times the tangent inverse of 1 plus a log, or excuse me, minus a log of 2. Okay, that's a number you have to get off your calculator. The rest of what I want to focus in on is some work with the derivatives. When you differentiate this, the derivative of tangent inverse is 1 over u squared, 1 over 1 plus u squared times the derivative of u. In this case, my u is equal to this right here, 1 plus, or x plus 1. What happens when you differentiate the log term? Yeah, so, yeah, it's going to be, this whole term is the u, so it's going to be 1 over u times the derivative of u. So I've got both of those things here. Now there's a little bit of algebra that's going to be required to get from here to here. You're going to have to get common denominators. Actually, you do have common denominators, because when you square this out and add 1, you're going to have common denominators. But you're going to have to distribute the negative and collect like terms. This is your first derivative. If you don't believe me, ask Wolfram Alpha. So there's h prime. H double prime, boy, it's just a big pain. Here's h double prime. But what can we figure out now that we have the first and second derivative? What's the first derivative going to tell us? Where the function's increasing and decreasing. So what about this tells me where the function's increasing and decreasing? What do I have to do? Yeah, I want to find out where the numerator equals 0 or where the denominator equals 0. But the denominator is really this term. It's 1 plus x plus 1 squared. I know it looks like that. It's written like that. But it's also equivalent to this. This can never be 0. Because you have something squared, which is going to be positive or 0. And then you're adding 1. So it's always going to be greater than or equal 0. So this can't, the denominator can't equal 0. But how about the numerator? Yeah. So h prime of x equals 0 really means that 5 minus 2x equals 0, or x equals 5 over 2. So let's put that down here. 5 over 2, x, f prime. At 5 over 2, the function is at 0. Numerically, you can actually figure out the y-coordinate. The y-coordinate turns out to be about 6.46. You're going to want that because you're going to need to put that point on your graph. Then what do I have to do? Yeah, I need to test some values, right? So I need to test a value to the left of this and to the right of this. What would be some good values? 2 and 3. Sure, 2 and 3. I don't think we need to take out our graphing calculus. Let's just work with the numerator. The denominator is already positive. So if I put in a 2 here, is the sign of this going to be positive or negative? Eric? And at 3? Negative. Good. So positive, then negative, increasing, then decreasing. What does that tell me about 5/2 as a point here? It's a max. Good. This is a max. That should be reflected on our graph. Let's go over to this one. The second derivative tells us about the shape of the graph. It's concavity. Well, I need to know where this can change signs. It can change signs where the denominator equals 0 or where the numerator equals 0. The denominator can't equal 0. So I'm just left with where the numerator equals 0. How am I going to figure out where the numerator equals 0? I don't think that factors. Quadratic formula. You can complete the square, sure. It will give you the same thing the quadratic formula will do. Just FYI, you could also use Newton's method. All right, we probably want a nice actual expression for the answer rather than a numerical answer. But you could and should use the quadratic formula here. X squared minus 5x minus 7 equals 0. means x equals the negative of -5 plus or minus the square root of -5 squared minus 4 times a, which is 1 times c, oxygen bottle please, over 2 times 1. Wow. Guess what you get? There we go. 5 plus or minus the square root of 53 over 2. Wow, isn't that special? Woohoo! Yeah, outstanding. All right. Well, let's come up with some numerical values for those. Because if you're like me, I don't know what that is numerically. I mean, where are you going to test points? I mean, what test point are you going to use for here? So we're going to put in these two values, make ourselves a little chart, x, f, f double prime. One of these, well, this would have to be 5 minus the square root of 53 over 2. And this one would be 5 plus the square root of 53 over 2. Second derivative of those points are 0. Might actually want the values here as well. So let's do this. Let's go to the home screen. I'll do 5 minus the square root of 53. Oops, I don't want that underneath here. Divided by 2. Now I've already typed one of these in. Here's a quick trick for you. Hit the second key, then the enter key. That'll bring up your previous calculation. Now let's just lazily go back here and change that minus to a plus. Boom, I got them both. So that's kind of nice. So about negative 1.14 and 6.14. Okay, I get it. If I wanted to find the y coordinates, well, that's a little bit more of a hassle. We can come pretty close. Let's put the function into our calculators. So hit the y equals key, then type in a 7, second tangent inverse of x plus 1 minus the ln of x squared plus 2x plus 2, like that. And now I'm going to ask my calculator to do the dirty work for me. Once I get that entered, hit the second key, then go to the table function. Let's just enter in those approximate values. So it was like negative, I was positive 6 point something, 6.14. So 6.14 gives me about 6.07. So let's put that in here. 6.07. And then negative 1.14. 0.9931. So negative 0.9931. Negative 0.99. It's about negative 1, right? What are these points? These are points where the concavity can change. Not necessarily maximum or minimums, but inflection points. An inflection point is where the concavity changes. All right. There's one last thing that I need to do. And that would be to test the signs here. Boy. Gee, isn't this fun? I get to go back now and enter in the form of the second derivative. Actually, you know what? If I wanted to be really lazy about this, deciding where the second derivative is positive and negative, I don't have to enter in the whole function if I'm just testing signs. Because the denominator here is always positive, so that's not going to change anything. The 2 is always positive. Really, the only thing I have to do is test this. And it's going to test out this way. Positive, negative, positive. So That's telling me my function is concave up, concave down, concave up. Wow. Let's bring that back and look at the graph now. First things first, we see that we've got a maximum point right here where we expected it, right? At 5 halves. 5 halves, you plug that in, you get a numerical value of about 6.463. Okay, that's our maximum. So let's label that max. There's a couple other points on our graph as well. This one out here, boy, I defy anyone to figure that out without calculus. What's happening at this point here, which has coordinates of, yeah, it's about, what was it, 6.14? Was that it? Yeah. 6.14 and 6.07. This is an inflection point. It's where the graph changes from concave down back to concave up. Not that you'd really be able to convince me of that with anything other than the calculus. It just doesn't really look dramatic there. It doesn't look like there's much of a change, but the calculus shows us that. So that's an inflection point, and this is an inflection point. So its coordinates were negative 1.14 and negative 0.99, and that's another inflection point. Wow. Nice. Yes, sir.
Is your first derivative, is that going to be always giving you like your maxes and minimums?
Yes. First derivative always tells you your maxes and mins, and the second derivative tells you where your function is concave up and concave down. Yep, always. Good. Whew. Okay. Wow. These are challenging. Any comments or thoughts on this one before we move on to the next one? Probably what I'm going to do here is I'm going to do as many as I can this morning, and then I'm going to do a slightly different set of problems this afternoon. And I'll put both videos online. That way, if you want more practice, if you want to see more of these problems worked out, you can go check it out. All right? So usually I give kind of the same performance in the morning that I do at the afternoon. Although you guys are my guinea pigs for my jokes. Whatever works in the morning, I use in the afternoon. If it's a dud, then I change it up a little bit. So I appreciate that. Thank you. All right, let's incentive for that. Yeah, compensation exactly. All right, let's see which one I want to finish up with. Well, I'll tell you what. This one, do you want to finish up with an easy one or a hard one? Because I mean, at the rate that we're going through these things, probably only going to be able to do one more. Do a hard one? You know, the one, I'm going to go back to kind of a theme that we've seen with a couple things here, and that is problem number 12, because it's going to require some careful work with the derivative. Let's see. We'll do the first part together, maybe the second part we'll let Wolfram Alpha do. So problem number 12. F of x is x times the square root of 9 minus x squared. Of course, a lot of you might right away write that as 9 minus x squared to the 1/2 power. What's the first thing we should look at? The domain, right? So we want to know what values of x we can and cannot put into this function. So, what's the big concern in working with a problem like this? It's not the x here. It's inside. What has to be true about what's inside? It has to be greater than 0. So, this can actually equal 0 at 3 and negative 3. So those are kind of the endpoints of things. Do I want things bigger than 3 and less than 3, or do I want what's in between? In between. So our domain is negative 3 to 3. And that's important because we don't want to be looking for critical values or inflection points outside of the domain. If you were really on the ball, you can notice that this is an odd function, but odd symmetry really isn't all that big of a deal for us. We don't have to worry about any vertical asymptotes, any horizontal asymptotes. You can find the intercept, for instance, the Y-intercept, and for that matter, one of the X-intercepts. If you did f of 0, what would f of 0 equal? 0. Thank you. F of 0 is 0. But let's just jump to the meat of this, which is working with the derivative. F of x is x times 9 minus x squared raised to the 1/2. This is going to require the product rule to differentiate this. So f prime of x is going to be u prime v plus v prime u. 1 times 9 minus x squared to the 1/2 plus derivative of the first times the second, derivative of the second times the first. So the derivative of this is going to be 1/2 times 9 minus x squared to the minus 1/2. But I hope you don't stop here. What else do I need, Sarah? Good. Times the derivative of the inside. Derivative of the outside times the derivative of the inside. Now the 1/2 and the negative 2 will cancel, give me a negative 1. And then the x and the x will give me an x squared. So let's rewrite this, clean it up a little bit. 9 minus x squared to the 1/2 minus x squared, 9 minus x squared to the negative 1/2. I think you know what's coming next, right? We've seen this 4 times before. Factor out which term? Perfect. So of these two terms that are in common, choose the one with the smallest exponent and factor that out. So we're going to factor out 9 minus x squared to the minus 1/2. And that means I need to divide both of these terms by that factor. Now, cleaning this up is your job. I'll give you a minute to kind of catch up here. I'm going to go over to Wolfram Alpha to speed things up and calculate the second derivative here. You would do well to maybe look at calculating the second derivative, maybe practice calculating it at home, because it's going to give you one more chance to work with factoring out these terms that have negative exponents. All right. So has everyone got that copied? I'm going to make a little switch over here, kind of cheat a little bit. So I want the derivative of x, 9 minus x raised to the 0.5 power, comma x, comma x again. Oh, thank you. X squared. I think that's got it. Raise it. Yeah, I forgot to raise it. All right, thank you. Raise to the 0.5 power. Okay, nice. Let's go back and see what you simplified, what you got when you worked on this. Now, the nice thing for us in this expression is that this cancels out altogether, right? What happens here? So this is going to, when you subtract the exponents, you get 1/2 minus negative 1/2 is 1. So 9 minus x squared to the first power minus x squared. These are like terms. Minus x squared and minus x squared gives you minus 2x squared. So 9 minus 2x squared over 9 minus x squared to the 1/2. All right, so that's f prime of x. 9 minus 2x squared over 9 minus x squared to the 1/2. I need to know where this can change signs. In general, where is this going to change signs? Aldine? Where could it change signs in general terms? Got some help up here for you?
Yeah, where the numerator or denominator.
Good. So where the numerator equals 0, so 9 minus 2x squared equals 0, or where the denominator equals 0. 9 minus x squared to the 1/2 equals 0. Now this is going to equal 0 at what 2 points? Can you just see them based on what's inside here? Yeah, 3 and -3. 3 and -3. But those are at the edges of your domain. You're not going to get any change of sign at the edge of your domain. So we're going to ignore these. I'm not going to worry about those. The ones that we're worried about are right over here. So it's 9 equals 2x squared. 9/2 equals x squared. Plus or minus the square root of 9/2 is x. And you can fiddle with that a little bit. You can rationalize the denominator, etc. I'm not worried about that part right now. Let's make ourselves a little bit of a chart here. So at negative square root of 9/2 and positive square root of 9/2, we've got x, f, f prime. The derivative is 0 here, so you should have a nice smooth function there with a tangent line that's horizontal at these points. Let's see, if you plug this in, I think you're going to get 9/2. Excuse me, no, negative 9/2 and 9/2 respectively. You might need and want to get a calculator out to find the value of this. I don't know what it's going to be. A little bit over 2, I guess. What is it? 2 point what? 121? All right, well, it'd be negative 1.21. Is that right? Okay, thank you. So what do we need then? We need to test some points. And in the sake of expediency, I think it's going to be negative, positive, negative. Like that. So it's telling us the function is decreasing, increasing, and decreasing. In particular, what kind of a point is this one right here then? A minimum. And the other one has to be a maximum. All right. We're going to cheat now and use the form of the second derivative given to us by Wolfram Alpha. F double prime of x. Now, if you didn't have that around, you'd have to use the quotient rule. And you'd still have to do some of that bonus factoring. If it makes you feel any better, I did it by hand this morning, bright and early. I did get the same thing. I just didn't have enough time to put that into our handout. So f double prime of x is x times 2x squared minus 27 over 9 minus x squared to the 3/2. So you can see that along the way in calculating the second derivative, you've got some cancellation there. Let me go back here then. Same question as before. I need to know where the numerator equals 0 and where the denominator equals 0. So what about the denominator equals 0? What can you tell me there? Yeah, 3 and -3. But since those are at the edge of the domain, we're not going to get any change of sign there. So We'll ignore these. Let's work on where the numerator equals 0. So x times 2x squared minus 27 equals 0. We got a couple possibilities. The nice thing for us is that one of them is pretty simple. X equals 0. The other one, where does this equal 0? It's where x squared equals 27 over 2. X equals plus or minus the square root of that. You know, I'm not necessarily a calculating genius, but I think I can safely bet that this is going to be bigger than 3 or less than negative 3. What's the relevance of that observation? It's outside of the domain. So we're going to ignore these parts, these 2 points. For us, the only place where this effectively can change signs is at 0. So x, f, f double prime, 0, 0. And to the left of this is going to be positive and then negative, telling us that the function is concave up and then concave down. Yeah, that didn't turn out too good. Let's try it again. Concave up and concave down. Wow, lots of information. Let's put that all together. If you take out your graphing calculator, you can graph this. One thing that you'll see is that the function at x equals 3, in fact, we can figure this out. What's going to happen when I put in a 3 into the function? It's going to be 0. At 3 and negative 3, you're going to be 0. So we've got these 2 points right on the axes, 3 and at negative 3. At this point, we knew we had a minimum. At this point, we knew we had a maximum. At 0, which is another known point, we knew we had an inflection point. So the rest of this is just connecting the dots in between. So like this and like this. So the function's concave up in that area. And then over here, it's concave down. Isn't that special? Go blue. See ya!